Good afternoon and welcome to the American Floral Endowment's Grow Pro webinar series. I am your moderator for this webinar. My name is Dr. Melinda Knuth. I'm an assistant professor at North Carolina State University, investigating consumer attitudes and behaviors for edible and ornamental horticulture crops. Today's session is on calculating the cost of LED lighting. On behalf of the endowment, I'm excited to be a part of American Flower Endowment's Grow Pro webinar series that features a new topic each month presented by an industry expert. The webinars are free to everyone thanks to the generous support of AFE sponsors. This session is sponsored by Fluence Bioengineering. Fluence Bioengineering creates lighting solutions for controlled environment commercial crop production. If you'd like to learn more about our sponsors, or if you're a supplier and interested in becoming a sponsor for a topic, you can find more information on AFE's website at endowment.org/growpro. Today's session was pre-recorded in English by Dr. Marc van Iersel. After the presentation, we will have a question and answer. Please feel free to submit your questions through the question and answer feature or through the chat at any time. We'll answer as many as we can before the end of the hour, and any unanswered questions will be answered through a separate email exchange. This session is being recorded and will be shared to AFE's YouTube channel. Through YouTube's accessibility features, you can also access the closed captionings in other languages. To get us started, I'd like to share a bit more about today's expert speaker, Dr. Marc van Iersel. Marc van Iersel's research focuses on cost-effective supplemental lighting technologies in greenhouses and vertical farms. He's the director of Project LAMP, a $5 million US-based research project that brings together plant scientists, engineers, and economists to develop profitable supplemental lighting strategies. Dr. van Iersel has published more than 150 scientific papers and has given invited lectures about his research around the world. Marc, welcome, and thank you for presenting today on calculating the cost of LED lighting.
Thank you for that introduction, Melinda, and I'm pleased to give this seminar today about a new tool that we have developed to help you estimate the cost of supplemental lighting, mainly in greenhouses, but also in plant factories. This work was done largely by colleagues in the Department of Management Information Systems at the university as part of a USDA-funded project that focuses on optimizing lighting in controlled environment agriculture. So let's start off by first talking why this research related to lighting is so important. If you are using supplemental lighting and you are in charge of paying the electricity bills, you undoubtedly know that the cost associated with supplemental lighting can be very high. And there are really two components to that cost of supplemental lighting systems. The first one is the capital expense, or the money that it takes to actually install the lighting system. And one of the first decisions that you have to make when you start thinking about a lighting system is whether or not you want to use HPS or LED fixtures. The advantage of HPS fixtures is that those are less expensive, but on the other hand, they use more energy. So LEDs have higher efficacy, or they produce more light with the same amount of energy. So that trade-off between HPS and LEDs can be fairly complicated. And getting that choice right is important because the operating expenses, basically what you pay for the electricity to run your lighting system, that can be high as well. And in many cases, that may actually account for 10 to 30% of the total operating expenses that you have in running a facility. So making the wrong choice here can have a really negative impact on the bottom line. So before getting into the nitty-gritty of how we can actually estimate what the cost of this supplemental lighting is going to be, I think it is important that we start off by defining a few basic terms related to lighting. And first of all, that relates to how we actually measure light in horticulture. So when you are talking to a lighting company and, for example, discussing a design, make sure that the information that you get from that lighting company um, is in the appropriate unit. So light levels really need to be measured in micromoles per square meter per second. And sometimes I still see references to foot candles, lux, or lumens, and that is just not appropriate for horticultural lighting. And if you are working with a company that uses foot candles or similar units, my suggestion would be that you try to find another company that uses micromoles per square meter per second in developing a lighting plan for your facility. Some of the terms that you will run into include PAR, PPF, PPFD, DLI, and it can be pretty confusing to keep these terms straight because especially the first three of them are sometimes used interchangeably. PAR stands for photosynthetically active radiation, and that is very similar to the visible part of the light spectrum, and it refers to the light that plants can actually use for photosynthesis. The photosynthetic photon flux, as is illustrated in this diagram, most commonly refers to the total amount of light that is emitted by a light fixture in 1 second, as you can see in this diagram right here, while photosynthetic photon flux density, as you can see here, that is the total amount of light that you receive in a 1 square meter area, as you can see right here, in 1 second. So for quantifying the performance of light fixtures, the photosynthetic photon flux is more important, but for determining how lighting is going to impact your crop, the photosynthetic photon flux density is more important. Both of these terms have their use, but they are substantially different, and understanding that difference is important. And so if you have some kind of a PAR meter or a quantum sensor, those are different terms to measure the light in horticultural facilities. What you are normally measuring is the photosynthetic photon flux density in micromoles per square meter per second. And then if you have a sensor that is connected to some kind of a data collection system, you can measure the PPFD over the course of an entire day, and then hopefully you have a system that can integrate all of these measurements that you get throughout the day. And if you add all of those up together, you get the daily light integral. And the daily light integral is really important because typically when we make recommendations for how much light to provide to different crops, those recommendations are made in terms of the daily light integral, and the units of that are moles per square meter per day. And so the real topic that I want to talk about today is various tools that we have developed to help you estimate the cost of different lighting systems. And we have one calculator that is an Excel spreadsheet that can help you estimate how many light fixtures you need, how much that is going to cost. You can compare different lighting systems and get a rough estimate of operating costs, but also the payback time. How long does it take to pay for a more efficient lighting system? So this calculator is available in Excel format. So let me go ahead and swap to that Excel file. So this spreadsheet was developed by Neil Madsen at Cornell University, who is part of the team that is working on this grant. And this is a pretty easy to use spreadsheet where you can provide some basic information, and then return the spreadsheet provides you a lot of valuable information. So the information that you can enter is in the yellow boxes right here. And I'll go through this one box at a time. So you can specify how much light your lighting system can provide. So in this example, that is 200 micromoles per square meter per second. And the power consumption of an individual lamp or fixture. So here we have 1090 watts. That is typical for a 1000 watt high pressure sodium light. They use a little bit more than 1000 watts. The size of your facility, so in this case, we have 43,560 square feet or 1 acre. You need to enter the efficacy of your light fixture. That is the amount of light that the fixture provides per unit energy. And so 1.8 is basically the efficacy of a very good high pressure sodium light. The percent of light that is lost from edge effects refers to how much light is actually spilling out of your greenhouse. And so if you have a 1 acre greenhouse, the amount of light that you end up losing is probably going to be pretty low. So that would be 3%. If you're doing calculations, for example, for a vertical farm, that percent light loss would typically be much higher. You then need to estimate how many hours per year you are likely to use your lighting system. So the default value here is 2,000, but you can easily adjust that. Your electricity price, so 16 cents per kilowatt hour in this example, and the cost of an individual lights fixture. And when you enter all of that, the information that is returned to you is shown in the red boxes right here. We have the number of square meters that are being lit. So that is equivalent here to 1 acre, just over 4,000 square meters. The amount of light that is produced by one individual fixture, the number of light fixtures that you need without taking into account the edge effects or the light losses that you have spilling out of your greenhouse facility, and the number of light fixtures that you need, taking into account that some of the light is actually going to be lost, the total cost of the light fixtures. So that is $150,000 in this particular example, close to it. The total amount of energy that is used over the course of a year. And then in this different color, I just made that a different color because it's by far the most important box in my mind, the electricity cost. So it's going to cost $150,000 roughly to operate these lights in this 1 acre facility. Those values are also provided per square foot and per square meter, but this value here, the 148,000, is the most relevant because that takes into account the size of your facility. What Neil Madsen also did is you can see at the bottom here tabs that are labeled lamp 1 and lamp 2. This allows you to compare two different kinds of light fixtures. So let me start actually by going to lamp 2. There we go. So here we have a somewhat similar setup with the same total light intensity provided by the supplemental lighting system. But now, rather than looking at high pressure sodium lights, we have an LED fixture here. It uses less energy to produce a similar amount of light as the high pressure sodium fixture, so 581 watts. And that higher efficiency is reflected here in this higher photosynthetic photon efficacy. This is basically a value of the efficiency of the light fixture. So this would be a very efficient light fixture. And all of the other numbers are the same. But now, rather than having a $140,000 or $150,000 electricity cost per year, that cost is reduced significantly because these lights are more efficient. Now, if I go to the lamp 1 tab at the bottom, this basically here has the same information as what we had previously for a high pressure sodium light. So the same power consumption, the same efficacy, the same calculations. But now when you scroll all the way to the bottom, it does a comparison between the two different kinds of lamps. So the cost per square foot to buy the high pressure sodium lights is going to be $3.42 per square foot, while for the LED fixtures, it is a little bit over $9 per square foot. But the electricity cost for the LED fixture is just under $2 per square foot per year, while for the HPS, it is $3.41 per square foot per year. And the spreadsheet then provides a rough estimate of what the payback time is for the more expensive but also more efficient LED fixture. So in this particular example, the estimate is that the LED fixtures would pay for themselves in about 4 years' time compared to the high pressure sodium. but it's very easy to run through different scenarios with this spreadsheet. So if we go to lamp 2 tab again, and we can change any of these values. So let's assume that you are going to get a rebate from your utility company to buy LED fixtures rather than high pressure sodium fixtures. And so that might change the cost of your light fixtures from $850 per fixture to, let's just assume, $550 per fixture. So if we change that here, all of the calculations get updated. We can go back to this page and we can look at the summary again. And now with that lower cost of the LED fixtures, it would take 1.7 years to pay for the more expensive but more efficient LED fixtures compared to high pressure sodium lights. One thing that I want to point out is that this spreadsheet currently does not account for the demand charge that you also have to pay to your utility company. And I'll get back to that in a minute, but the demand charge is associated with your peak power use within any billing cycle. And that demand charge is going to be lower with LED fixtures compared to high pressure sodium fixtures. And that would actually shorten the payback time for more efficient light fixtures. So that is something to keep in mind, and we hope to be able to update this spreadsheet by including the impact of the demand charge as well. So I'll switch back to my PowerPoint now to go over some of the other calculators we have developed. So the other tools that we have developed allow you to enter more specific information about your particular greenhouse location as well as configuration. And that provides more precise estimates of how much it is going to cost to operate the light fixtures. And so we have developed 3 different calculators. The first one we developed is a calculator that can estimate the electricity cost, assuming that you have a large enough lighting system installed to reach the target daily light integral that you want to achieve in your greenhouse every single day of the year. That calculator is available for use, but I'm actually not going to talk about that today because it is not realistic that you would actually design your lighting system to be able to reach the target daily light integral that you want to achieve on even the very darkest day of the year. So we have 2 more advanced and I think more useful calculators now, thanks to Jared Rennenberg, who actually did the coding to make this happening. So the second calculator that we have developed allows you to estimate the required capacity of your lighting system. How much light does your lighting system need to be able to provide so that you can reach the target daily light integral that you want to reach a certain number of days or a certain percentage of days of the year. And then the third calculator that we have is very similar, but it takes the opposite approach. You can specify the capacity of your lighting system, and in return, the calculator will then estimate how often, how many days a year you are likely to reach the target daily light integral. And both of these calculators 2 and 3 are going to be able to estimate the electricity cost, including the demand charge that is associated with that electricity use. So the demand charge is really important because in many cases, what you pay for the demand charge is in the same order of magnitude as the actual price of the electricity. So just to re-emphasize again, that demand charge is based typically on the 15 minutes in a 1-month period during which you use the most energy. And based on that energy use, your utility company is charging you quite a bit of money basically to provide the infrastructure that is required to get that electricity to you. So the basic idea behind how these calculators use is that you enter your zip code. That allows us to go to a database and figure out your location. Once we know your location, we go to a different database where we can get historical weather data that allows us to estimate how much sunlight you get in your specific location. You enter the transmission of your greenhouse. That allows us then to calculate how much of that sunlight that is available in your location actually gets into the greenhouse. And once we know how much light you get in the greenhouse and we know how much light you actually want, or the target daily light integral, we calculate how much supplemental lighting is needed. If we know how much light is needed and we know the efficacy of your lighting system, we can calculate the electricity use. And once we know the electricity use, we can calculate the cost of that electricity based on the specific price that you pay for the electricity in your particular location. So that just gives you a broad idea of how the calculator works. We don't collect any of this information. Everything that you enter is immediately deleted after you log off the site. We don't want to collect any information from you. So these calculators are available through this web page that is maintained by Project LAMP. We have an outreach page, and on that outreach page, we have a link to lighting calculators. So this is the full link for these calculators. And I'll go ahead and click on this, and then we'll go to that website. So from this website, you can calculate you can access the different calculators that we have developed. So if we scroll down a little bit, we see different calculators, including the how many fixtures do I need calculator. That is the spreadsheet developed by Neil Madsen. But what I would like to look at now is, first of all, the calculator that we developed that is going to estimate how large your lighting system should be so that you can reach the target daily light integral that you want a certain number of years. So we have a link here that takes us to that calculator. So I'm going to go ahead and open that. That takes us to a different website. It will take just a minute, well, a few seconds to load, not a minute. And so this is the calculator and the interface. We start off here at the top on the home page. We have instructions step by step on what to do. So next we go to the add location page. And so you can enter a name for your greenhouse. I'm going to just call it UGA because I'm at the University of Georgia. You enter your zip code, and I'm going to enter 49002. That is Kalamazoo, Michigan. An electricity rate of 12 cents per kilowatt hour. I save this information, and now it tells me that I can add my greenhouse design. So I go back to the top, click on add greenhouse design. I'm going to call my greenhouse greenhouse 12, and I'm going to say that my greenhouse is 363 feet long, 120 feet wide, and I picked those numbers because that ends up then being 1 acre. You have to specify the transmission of your greenhouse, and if you click on the arrow, it gives you some guidance. We're going to assume, let's say, a 60% transmission rate. A target daily light integral, if you're growing ornamentals, let's say that you may want the daily light integral of 12 moles per square meter per day. Let's assume that we have LED fixtures with an efficacy of 2.6 micromoles per joule, and you want to be able to reach the target daily light integral of 12 moles per square meter per day 80% of the days of the year. You're going to run your lights up to 16 hours a day. And so this box here is important. This is the demand charge. So your electricity bill should have a number on it that tells you what your demand charge is in dollars per kilowatt. $10 per kilowatt to $20 per kilowatt is pretty typical. And then one other thing that we can do, if we click on this gear icon, we can actually say, well, I want to light my whole greenhouse in January, February, March, and April. In May, I'm only going to light 50% of my greenhouse. In June, I don't need any light. In July, I don't need any light. In August, I don't need any light. And in September, maybe I'm just going to light 50% of the greenhouse. Then I click update percentages. And then we save this information at the bottom here. And that allows us then to go to the next step that is actually going to provide us the results. We need to click update here to actually get the results. And here they pop up. And so I'll talk you through what you see on the screen here. So in the on the top left, you see the information that you entered as a user. So the percent of your greenhouse facility that is going to get supplemental lighting, the specific information that you entered about your specific greenhouse configuration. Then at the top right, we have the annual cost of the electricity that is needed to operate these light fixtures. So we have here roughly $30,000 per acre in actual electricity cost. And then the demand charge in this example is another $12,000 per acre. So again, that is a number that is certainly not trivial. Let's take a look at this graph on the middle left. This shows typical sunlight data for this particular location. Again, this is for Kalamazoo, Michigan, over the course of an entire calendar year. On days that are shown in blue, you are going to get more sunlight in your greenhouse than what you actually need to grow this crop, more than 12 moles. So you don't need to provide any supplemental lighting. The days that are shown in red are days that you don't get 12 moles per square meter per day from the sun. And so you need to provide supplemental lighting on those days. When we then look at the graph on the right, this shows how much supplemental light is needed on different days of the year. So at the bottom here, we see all of the days on which supplemental light is not needed. And everything that is above zero indicates that we do need to provide supplemental lighting and how much supplemental lighting is needed on different days. This line right here actually shows how much supplemental lighting is needed to get to that daily light integral of 12 moles per square meter per day on 80% of the days of the year. And at the bottom right here, you can see that you need to install a lighting system that can provide 5.5 moles per square meter per day. And if you run your light 16 hours a day, that basically means that you need an instantaneous ppfd from your lighting system of 96 micromoles per square meter per second. And so the data points that you see above this red line in the graph, those are days that you are not going to reach your target daily light integral. So you're going to have a shortfall 20% of the days of the year. This graph is actually interactive. So if I click in here, I can adjust the capacity of the supplemental lighting system. So let me go ahead and click adjust. And so now the capacity of the supplemental lighting system has increased to 7.5 moles per square meter per day. And that tells us now that we can reach our target daily light integral about 90% of the time. So we would have a shortfall of roughly 37 days of the year, and the rest of the time we can achieve the target light levels. But now you need to install a lighting system that can provide 130 micromoles per square meter per second. And the cost of running that lighting system has increased to almost $36,000 for the electricity and $16,000 for the demand charge associated with that. So in total, this would be just over $50,000 per acre. You can also go back to different parts of the calculator. So let me go back to the add greenhouse design. And let's say that instead of having HPS, we now want to do instead of LEDs, we now want to do HPS. And we have a light fixture efficacy of 1.8 micromoles per joule. We save that. We go back to the amount to the results, and I need to update that now. And so now it has redone all of these same calculations, but now using information from HPS fixture, and you can see that now the electricity cost has increased to almost $52,000, while the demand charge is $23,000 per year, which means that total that's about $75,000 to provide that amount of light with HPS fixtures. You also get some estimates on the bottom left here for how much that lighting is going to cost on a weekly basis, and this is available for the entire year. If you want to, you can download these results to a file that you can open in Excel, but that is probably only of much interest to consultants. Let me go ahead and close this. Okay, so now we're back on the website, and I'll scroll down again. And so the other calculator that I think will be useful to the greenhouse industry is the calculator where you can enter the specific design of your lighting system, and this calculator will help you determine how often you will actually reach your target DLI based on that specific design, as well as estimate the electricity cost, including the demand charge. So let me go ahead and open this calculator. And this calculator requires a lot of very similar information as the previous one. So again, we have similar tabs here at the top. So I'll click again on add location. I'll add the same information here, the same zip code, which was 49002, Kalamazoo. I don't recall the electricity rate I used last time, but we'll make it 12 cents per kilowatt hour. We save this. And then when we go to the greenhouse design here, the information that is needed is a little bit different. But again, you provide a name for that specific greenhouse, the size of the greenhouse, and I will once again just go with a 1 acre greenhouse here for simplicity. We'll go with 70% light transmission, a target daily light integral. We'll just go with 12 again. The efficacy, 2.6 micromoles per joule. And so this is different information. So here you need to specify how much light your supplemental lighting system can actually provide. And the company that installed your lighting system should be able to tell you this. So let's go ahead and we'll assume that you have a lighting system that can provide a PPFD of 100 micromoles per square meter per second. You are going to run that lighting system for up to 16 hours per day. And we'll go with the demand charge cost here of $12 per kilowatt. Just like previously, if you want to, you can change which months of the year you actually light. So I'll just go ahead and turn the lights off in July. And then we save this information. This tells us that with this particular lighting system, we can provide a supplemental daily light integral of just under 6 moles per square meter per day. We scroll back to the top, go to days on target now, and click update like we did before. And so here we have very similar information as before, with near the top center here, the information that you entered. So that just allows you to double check to make sure that you entered all of the information correctly. We have the estimate of the electricity cost, which is in this particular example, $27,000 per year, plus a $20,000 demand charge that comes along with that. So just under $50,000 per year. The graph on the left is the same as it was in the other calculator. It shows how much light you can expect to get in your greenhouse from the sun, with this red line here indicated your target daily light integral, in this example 12 moles per square meter per day. And again, this graph is also very similar to what we saw previously, where the red dots indicate days on which you are not able to reach your target daily light integral of 12 moles per square meters per day, because your lighting system just doesn't have enough capacity. And so what this also shows here is that you are going to reach your target daily light integral in a typical year 85% of the time, or 310 days out of the year. And here we summarize the total amount of light that your lighting system can provide within a single day. Like with the previous calculator, you can download the results if you want to an Excel file, but once again, that is probably not of much interest to most people. So again, this is the web page through which you can access all of these various calculators. The link will be shared with you in the chat, so you have access to this. If you have any feedback on the calculators, please let us know at info@hotlamp.org. We love feedback, and if we can make these calculators better for you, then we will gladly do so. With that, I would like to wrap up my presentation and start the Q&A. I would like to acknowledge the USDA NIFA Specialty Crop Research Initiative grant for sponsoring this research. And I would like to thank the American Floral Endowment for organizing this webinar today. And just as a heads up, before I sign off, I would like to make you aware of next month's webinar that will be given by Michelle Jones from Ohio State University. She has done a lot of really interesting work related to biostimulants, and she is going to discuss some of the benefits that you can get from using biostimulants in floriculture. Thank you for your attention, and I look forward to the discussion.
All right, thank you, Marc, for your presentation. I'd like to open up the session for question and answer. And we have one in the chat, and it says, could we use the spreadsheet application in Canada?
So the spreadsheet in principle can be used in Canada if you can find a database with the light data that you need to put into the spreadsheet. I saw the question. I was trying to find online whether or not there is a database. I was not able to find it right away. But if you have light data for Canada, then the spreadsheet can be used. The online app right now only works in the US, but I will see if we can create a version that would work in Canada as well.
Wonderful. Another question we have is, what is the best way to measure light transmission in a greenhouse?
Yeah, so light transmission is something that many growers don't really know. So the best way to measure that would be on a sunny day, preferably during the middle of the day. You take a light reading outside, and then you take a few light readings inside of your greenhouse. And you need a few readings in the greenhouse because the readings may vary a little bit in the greenhouse. But then you take the average light level that you have inside of your greenhouse, and you divide that by the light level that you have outside of the greenhouse. And that is your light transmission.
Okay. The next question we have is, does the calculator work in countries other than the US? So we kind of touched on this a little bit before.
Yes, and so right now it doesn't. But we are making the code for these calculators publicly available. And so if someone can find a database that allows the software to find the location and corresponding weather data, it should be relatively easy for someone with the right programming skills to take this calculator and adapt it so that it can be used in other countries.
Okay, another question we have is, could the calculation sheets be adapted to vertical farming with no natural sunlight?
So the spreadsheet that I showed with the two different lamp types in it, that can be used to look at vertical farming applications. We thought about creating a version of the online app for vertical farming, but it turned out that that would essentially turn into the same thing as the spreadsheet that Neil Madsen already developed. But yes, that Excel spreadsheet from Neil Madsen can definitely be used for vertical farming.
Okay, I tried using the calculator, but it keeps crashing. Any idea what the problem may be?
Um, I've run into that same problem myself. If I use the zip code for my home, the calculator does not work. There seems to be an issue that with some zip codes, the app is unable to actually find your location and then nothing else works anymore. So if that happens, the best solution is to use a different zip code from a nearby location, and hopefully that'll fix the problem. If that keeps happening, please let us know and we'll see if we can fix it.
Okay. How do I find a good target daily light integral for my crop?
So yeah, that's a good question. Different crops do need different amounts of light. So there are a number of different extension publications available that give recommendations for a wide range of different crops. Purdue Extension probably published the most extensive list of DLI recommendations for many different crops. Um, I wish I had a link for that ready, but it was written by Roberto Lopez while he was still at Purdue University.
Could you talk a little bit about the underlining assumptions for the calculator?
Sure. So the most important assumptions are, first of all, that you have a supplemental lighting control system that can make sure that every day of the year you provide just enough light to reach your target daily light integral, but not more than that. And the second thing that is really important to keep in mind is that we are using historical weather data for these calculations. For the simple reason that we don't know future weather data, obviously. So that's the best we can do. But of course, your weather may not be the same as what it has been in the past. I think averaged over the entire year, the sunlight is probably going to be pretty similar from year to year. But when you look at the weekly lighting costs, those may come out to be substantially different from what our calculator predicts just because your weather conditions may not match this historical data set.
Okay, and if anyone has any more questions, please put them in the chat. We have one last question left. Is there anything I can do to reduce the demand charge?
Yes, so the demand charge is a tricky thing, and I've heard actually from quite a few growers that they are more concerned in many cases about the demand charge than the actually cost of the electricity. And so that demand charge is based on the peak power use that you have during any 15-minute period within a single billing cycle. So if at all possible, if you have your lights on at full power, and that is going to use a lot of electricity, you would ideally cut out or turn off any other equipment that you may have that is also drawing quite a bit of electricity, because the key is simply to reduce that peak power use. So that may not be simple, but if you have other equipment running that uses a lot of electricity, see if you can minimize the use of that equipment while the lights are fully powered.
Wonderful. Well, that is all the questions that we have. If there are no more questions, then I think we will end the session. So thank you for joining us today for another session of AFE's Grow Pro webinar series. Join us next month for Dr. Michelle Jones' presentation on the use of biostimulants in floriculture production, which is on April 19th at 1 p.m. Eastern. You can register at endowment.org/growpro. If you're there, check out our past webinar recordings, other grower related resources, and research reports available to you free thanks to industry support. We ask that you please complete a brief survey about today's session where you can suggest additional topics and help us continue to improve these webinars. Thank you again for joining us and have a great day.